Thank you, Todd, for the introduction. Hey, good morning, everyone. I'm glad to be here. Today, I'm going to talk about some of my research on soil nitrous oxide emissions and how these studies can help us to develop nutrient management. I was born in a remote village in southwest of China. Excuse me. During the time I grew up, I worked a lot with my parents in the field. Back then, all the field work was conducted by hand. Everyone in my family worked very hard, but we barely had enough food. So my parents' big wish for me was to leave the farm and don't do anything about farming. But you know, kids always go against their parents' wish. Years later, I learned that if someone had taught us how to manage our farm in a sustainable way, we would not be hungry. So to help more people to avoid hunger, I followed my heart and became a soil scientist. Here is my journey. After I grew up in my farm, in my hometown, I went to northeast China to get my bachelor's and master's in soil ecology by studying nutrient management in corn, soil, wheat systems. And after getting bachelor and master's degree, I went to, I went to Tibet to have my PhD program on nitrogen balance and carbon stability in wetland and grassland ecosystems. Meanwhile, I also have my PhD program on nitrogen biogeochemistry in California, where I also have my postdoc training on the management of organic waste. Today, I'm here in Lexington to present some of my research. So in this talk, I'm going to start with the background on nitrogen cycle and nitrous oxide emissions. I will discuss the mechanisms and the factors controlling soil nitrous oxide and what the implications for nutrient management. After that, I will introduce some of my ongoing work on COMET-Farm and the Disney model, and I will end this talk with my vision for the position as a soil scientist. So let's look at the nitrogen cycle in the soil. This, excuse me. So in this diagram shows the nitrogen cycle between atmosphere and the soil. So first we can say in the atmosphere, nitrogen gas can be fixed through microorganisms to convert to organic nitrogen, and organic nitrogen can be converted to ammonia, which can be used by crops. And meanwhile, nitrogen gas in the atmosphere can also be converted to ammonia fertilizer through industrial manufacture. After ammonia being applied into the soil, it can be converted to nitrate, and the nitrate can be denitrified to produce the nitrogen gas and then return to the atmosphere. During the process of ammonia converting to nitrate to nitrogen gas, nitrous oxide can be produced and released into the atmosphere and leak out from this cycle. So why we care about nitrous oxide? So first we can say nitrous oxide is a potent greenhouse gas that has 300 times the global warming potential as carbon dioxide. And also, this diagram shows the nitrous oxide concentrations in the atmosphere. From this graph, we can say, in the recent years, the nitrous oxide concentration in the atmosphere increased dramatically. In US, nitrous oxide consists of 50% of the total greenhouse gas emissions in agriculture sector, and the majority of these emissions are associated with soil management. In agricultural soil, there are many factors that can affect nitrous oxide emissions. There are, for example, oxygen availability, water content, nitrogen availability, temperature, metal, pH, soil texture, especially soil clay content, and organic carbon. All these factors can affect nitrous oxide emissions directly or through the impact on the activities of nitrifier and denitrifiers, and then contribute to nitrous oxide emissions. The management practices such as tillage, irrigation, fertilization, cover crop, and organic amendments, they can contribute to nitrous oxide emissions through the impact on these factors. So in this talk, I'm going to focus on the factors of oxygen. Oops. Excuse me. The factors of oxygen and nitrogen availability. Excuse me again. And the management practices of fertilization and organic amendment. So to understand the mechanisms of nitrous oxide emissions, we need to understand the pathways of nitrous oxide production. So in soils, there are many factors that can contribute to nitrous oxide emissions. For example, nitrifier, nitrification, nitrifier denitrification, and nitrification coupled denitrification, and heterotrophic denitrification. Among these pathways, nitrifier nitrification, nitrifier denitrification, and nitrification coupled denitrification, together we named it ammonia oxidation, because all these three pathways started with ammonia convert to hydroxylamine. This is ammonia oxidation, so we call it ammonia oxidation pathways. So to separate different nitrous oxide production pathways, here I used dual isotope to separate nitrous oxide from each pathway. First, I labeled M15 in the ammonia and M15 in nitrate to separate nitrous oxide emissions from ammonia oxidation and heterotrophic denitrification. But next I used based on the oxygen source in the nitrous oxide from either oxygen or oxygen in the air or oxygen in the water. I labeled oxygen 18 in water to separate nitrous oxide emissions from nitrifier nitrification and nitrifier denitrification and nitrification coupled denitrification. By using this dual isotope method, I tested the hypothesis of nitrous oxide production increases as oxygen concentration decreases. Under low oxygen concentration, and nitrifier denitrification is the dominant pathway of nitrous oxide production. In this experiment, I incubated soil under different oxygen levels, and each treatment had 4 sub-treatments with different isotope labeled substrate. They are oxygen 18 in nitrate, oxygen 18 in water, M15 in ammonia, and M15 in nitrate. And I incubate the soil under 50% of water holding capacity, which was considered dry in the field condition. So here is the result. First, we can say as the oxygen concentration decreased, the production of nitrous oxide increased. And if we look into the contribution of different pathways to nitrous oxide emission, we can notice that if the oxygen concentration is around 21%, nitrification is a process to produce nitrous oxide. And if the oxygen concentration decreased from 21% to 3%, nitrification coupled denitrification start to kick in. If the oxygen concentration keep decrease from 3% to 0.5%, nitrifier denitrification is a main pathway to produce nitrous oxide. If there's no oxygen in the soil, heterotrophic denitrification is the only pathway that can produce nitrous oxide. So the finding of this study is nitrifier denitrification is a main pathway of nitrous oxide under low oxygen condition. This finding challenges the existing thoughts that denitrification is the only pathway that can produce nitrous oxide under limited oxygen condition. The effect of nitrogen substrate. This graph shows the relationship between nitrogen fertilizer rate and nitrous oxide emission. IPCC report assumed that 1% of the fertilizer rate, 1% of the applied fertilizer will be emitted as nitrous oxide. That is shown as this red line. However, recent years, more and more studies start to find if we applied more fertilizer, for example, 108 gram nitrogen per hectare, more than 1% of the applied nitrogen will be emitted as nitrous oxide. Since ammonia is the majority form of fertilizer that has been used in the US. So the question here is, how are ammonia concentration, nitrification rate, and nitrous oxide production how are they related? Does high ammonia concentration means high nitrification rate and therefore high nitrous oxide production? To answer this question, I conducted the lab incubation to incubate the soil under different ammonia concentrations. Here is the results. So in this graph, the x-axis represents the incubation time, y-axis represents nitrification rate, and the different bars represent different ammonia concentration. So firstly, we can say during the incubation time of 0 to 3 days, the nitrification rate didn't change, didn't increase as the ammonia concentration increased. And after 14 days of incubation, we can see the nitrification rate in the 200 and 1,000 milligram per kilogram treatment decreased. And even though we found that they still have a lot ammonia in the soil by the end of our incubation. So the question here is, why did the nitrification rate decrease even when the substrate was still plentiful? By revisiting the nitrification process, we know the first step is ammonia oxidation, which requires oxygen. So I assumed that the soil oxygen concentration must have changed during our incubation. So here are the results to support my assumption. From this graph, we can say over the incubation time, the concentration of oxygen in the soil decreased, and lower oxygen concentration was found in the soil, amended with higher ammonia concentration treatments. So that means in the higher ammonia concentration treatments, more oxygen was consumed. So the summary of this part of work: in the past years, I have found nitrous oxide from ammonia increased as oxygen concentration decreased, and nitrifier denitrification is the main pathway to produce nitrous oxide under low oxygen condition. And I also found a high soil ammonia concentration can promote the consumption of oxygen, which will increase nitrous oxide emissions. In the future, I would like to explore the mechanisms of ultrafiltration nitrifiers, the use of nitrite under limited oxygen condition. And also I would like to understand the ecological and agronomical and also I would like to understand the ecological and economical relevance of nitrifier denitrification. And this type of the work can be done in collaborations with other scientists like microbiologists and agronomists, rhizosphere scientists, and ecologists. So next part of my work focus on developing sustainable nutrient management. This part of the work includes the use of synthetic fertilizer and the use of organic waste. After we apply synthetic fertilizer to the soil, part of them will be used by crop to produce a good yield, which allows farmers to increase their income. Part of them will be lost as gas, which will cause climate change and air pollution. Part of them will move to water systems and decrease water quality. So, management practice, so developing sustainable nutrient management is a key to secure our future, the future of our agriculture in the aspect of increased crop yield and decreased environmental impact. Here I investigated nitrogen fertilizer rate and type in how they affect nitrous oxide emissions in California wheat cropping systems. So first we can say from when we applied the nitrogen fertilizer rate, when we applied from 0 to 168 ammonia sulfate, the nitrous oxide emissions increased. And more nitrous oxide was emitted from the treatment with anhydrous ammonia compared to ammonia sulfate. For the green yield, first we can say the green yield did not increase as the amount of fertilizer application increased, but we did get more green yield from the application of anhydrous ammonia compared to ammonia sulfate. So these results tell us when developing nutrient management, we need to consider the trade-off between green yield and environmental impact, in this case, nitrous oxide emission. In processing tomatoes, we got the similar results. First, when the nitrogen fertilizer application increased from 0 to 165 kilogram per hectare, nitrous oxide emissions did not increase that much, but it was boosted once the fertilizer rate over 165 kilogram per hectare. If we look into the tomato yield, the tomato yield was not increased if more than 165 kilogram per hectare of fertilizer increased. So these results tell us that when we decide how much fertilizer we put into our crop systems, we need to think about the crop nitrogen uptake. We want to apply what the plant needs, but we don't want to boost, we don't want to increase the environmental problems. The next part is the use of organic waste. So in the US, 28% of the yard trimming is 28% of the multiple solid waste is yard trimming and food waste. In California, currently we have this climate laws require us to divert this part of the organic waste from the landfill to composting to be able to reuse the nutrients in this part of the organic materials, and also to reduce the environmental impact of the landfilling. In California, after yard trimming are collected, they will be shipped to the nearby compost facility and then go through a standard composting procedure. After the compost is mature, which is about 8 to 12 weeks, and it can be used as organic amendments and applied into the cropping systems, and to increase soil organic carbon, water holding capacity, health, microbial activities, and hopefully to tighten nutrient cycle. But what we still need to know, what we still need to understand is the environmental impact of the whole process. Here I investigated the effect of compost application on nitrous oxide emissions in almond orchards and tomato fields. So let's first look at almond orchards. In almond orchards, we applied 3 tons per acre compost and also 6 tons per acre compost. And from this graph, we can see the application of compost did not increase nitrous oxide emissions compared to the control. And if we applied 3 tons per acre compost, and it has potential to decrease nitrous oxide emissions compared to the control. And in the tomato fields, the results are similar. Regardless of the seasons, so we measured the nitrous oxide in winters and also summer. So regardless of the season, the application of compost did not increase the nitrous oxide emissions compared to control. I also investigated the application methods. How did the application methods of green waste compost affect on nitrous oxide emissions? The application method here I investigated are surface application and incorporation into soil. So we have 4 treatments in the field, which we have control, no compost, control and tillage, and the surface application, which we just apply compost on the surface of soil, and incorporation into soil, which we tilled the compost into the soil. So here's the result. From this graph, we can say the nitrous oxide emissions from the treatment with incorporation has much lower nitrous oxide emissions compared to surface application. The reason for this probably because after we incorporate the soil, it promoted nitrogen immobilization in the soil, which reduced the substrate for nitrifiers or denitrifiers to produce nitrous oxide. And another part of a reason, probably because incorporating compost into the soil can create like extremely anoxic conditions, which will promote the consumption of nitrous oxide and then reduce the nitrous oxide emission. To be able to test the response of the different soil types to the application of compost, I collected 10 agricultural soils across California agricultural land and incubated in the lab with compost and ammonia or nitrate fertilizer and also different water levels. I also used the M15 method to label the different nitrogen pools to distinguish nitrous oxide emission sources. So here's the result. So this graph, the main point of this graph is the response of nitrous oxide emissions really depends on soil types. For example, in some soils, the application of compost decreased nitrous oxide emissions. But in other soils, the application of compost increased nitrous oxide emissions. To be able to tell why compost has such different impact on nitrous oxide emissions, I used the M15 to separate the nitrous oxide emissions from compost and pool and N2 from nitrous oxide from fertilizer pool and nitrous oxide from soil pool. From this graph, we can tell first, compost itself is a source of nitrous oxide emissions. And the application of compost increased nitrous oxide emissions from fertilizer pool if we apply ammonia sulfate. But it didn't affect nitrous oxide from fertilizer pool if we apply nitrate fertilizer. But and also the application of compost decreased nitrous oxide from the soil pool. These results tell us that if we apply the compost to the soil, which has a high background of nitrous oxide emissions, it could help us to reduce greenhouse gas emissions overall. Meanwhile, I also analyzed the soil factors that associate with nitrous oxide emissions from these 10 agricultural soils. And I ranked the contribution of different factors to nitrous oxide emissions. These factors are pH, dissolved organic carbon, total nitrogen, and also iron. So the values of any factor over this line, we consider is they have a significant contribution to nitrous oxide production. So first we can say the factors like pH and inorganic nitrogen, dissolved organic carbon, and also the sand content and clay content has a significant contribution to nitrous oxide emissions. And surprisingly, I found that iron is the most important factors among these factors to affect nitrous oxide emissions. Here, iron was attracted by pyrophosphate, represent the soil iron complexed with the soil organic matter. Summary of this part of work. So in the past years, first I have found nitrogen fertilizer type and rate, they have significant effect on crop yield and nitrous oxide emissions. And also I found the effect of organic waste on nitrous oxide depends on soil type and application method. And also I discovered the iron is one of the most important factors to affect nitrous oxide emission. In the future, I would like to explore the mechanisms of how does compost application method and rates affect nutrient loss and what's the implication for sustainable nutrient management. And I also want to understand how exactly does iron affect nitrous oxide production, and what's the relationship between iron, nitrogen transformations, and the soil carbon sequestration. Next is my ongoing work on COMET-Farm and Disney model. This work is in collaboration with Keith Postin in the Colorado State University and USDA Climate Hub in California. So COMET-Farm, what's COMET-Farm? COMET-Farm is a carbon management and estimation tool. It is a web-based full farm level and carbon and greenhouse gas accounting system. It accounts soil carbon and biomass carbon change, soil greenhouse gas emissions, greenhouse gas from livestock, and the carbon emissions from energy, and also other emissions such as burning and lambing. So the goal of COMET-Farm is to allow farmers to estimate the farm scale crop yield and the greenhouse gas emissions, and also help the growers to explore the yield and greenhouse gas impacts of the alternative management practices and land use strategies. And also this tool allowed us to adapt the model for new cropping systems and make the tool accessible to the public. So in California, currently we have 65% of crops can be modeled in this system. And currently we're working on to adding 15 specialty crops into our COMET-Farm system. These crops such as lettuce, tomato, cotton, and strawberries. And we have perennial crops like almond, walnuts, wine grapes. And after this effort, we estimate we are going to have 85% of the crops in California can be modeled into this system. And currently in California, there have some conservation districts are using COMET tool for carbon farming planning. And California Department of Food and Agriculture is also use COMET Planner, which is a simplified version of COMET-Farm for their healthy soil programs. So how does the COMET-Farm works? So in the web interface, users only need to input the information about location, about where are they field, and activities such as irrigation, tillage, and fertilization into the system. So after that, the system will pull out the relevant climate and the soil data and put all the data together to run the model. And after the model running, the system will produce a report that can be used by users very easily. So the basis of Disney model is the basis of the COMET-Farm is Disney model. So in this diagram, it shows like how this Disney model works. So in this model, first we can see they have a plant production submodule. Plant production will contribute to the soil organic matter pool, which will contribute the distribution of carbon into active pool, slow pool, or passive pool. And the soil organic matter pool, will control the availability of soil nutrients, which will contribute to trace gas fluxes as well as to plant productions. And the land use information such as vegetation type, nutrient, tillage, irrigation will change the flow of this process. And in this model, we are able to incorporate the soil process studies like our specific lab incubations, as well as field observations to improve the performance of the model. So here, this is an example for what the model output looks like. This is like for California almond. So we measured in the field. We measured the carbon content in the almonds, and also in the model we have this data generated based on the activities which we put into the model. So the x-axis represent the measured data, y-axis represent the modeled data. From this model, we can see like about 40% of the measured data can be predicted by model. It is not bad, but more work still needs to be done to improve the performance of the model. So, can we use COMET-Farm in Kentucky? So the answer is yes. So in Kentucky, first we can improve the COMET-Farm for hemp for the hemp cropping systems. We know Kentucky is the largest producer for the industrial hemp, and the nitrogen management is still a question right now. And also like in the COMET-Farm, we have the program to we have calibrate the Disney model for hemp already. I mean, which is only one study, which from the China, but since we have the program there, so we can use that for Kentucky. And also, given the fact that COMET-Farm also have the mode for the corn, wheat, and apple and peach, this kind of perennial crops, which we just improved the sub model for this perennial crops. So we can adapt and improve COMET-Farm for these crops in Kentucky for sure. And conclusions, in the past, I first understood the mechanisms behind nitrous oxide emissions, and then applied them to the use of synthetic fertilizer and organic compost on crop yield and nitrous oxide emissions. Currently, I'm working on incorporating both of the mechanism studies and field observations to a process-based model, and the outcome of the model will guide me to explore more nutrient management. My vision for the position include research objectives and approach. To secure the future of agriculture, we need to develop sustainable nutrient management to increase soil fertility and productivities. And that we need to ensure the social and economical impact of this management. With the goal of sustainability, we will also need to consider about the environmental impact of these management practices. Therefore, my long-term goal is to improve and advance alternative management to strengthen sustainability of cropping systems in Kentucky. To reach this long-term goal, there are 3 objectives. The first objective is to provide nutrient management practices that address nitrogen transformations, nitrogen availability, and soil carbon cycling. The second objective is to optimize these management practices to increase soil carbon sequestration, increase nutrient use efficiency, and crop yield without triggering environmental problems such as nutrient loss. The third objective is to improve management guidelines and effectively deliver them to stakeholders. My approach to fulfill these objectives include fundamental research on biochemical processes that in soil and rhizosphere, and also conduct the field research with a collaboration with growers, farmers, ranchers, and other stakeholders. After these 2 parts work done, I will improve the process-based model based on the results from fundamental research and field research. After the process-based model, I will develop improved best management practices to meet stakeholders' needs. One of the potential research programs I would like to develop in Kentucky is using organic amendments to increase soil productivity and enhance sustainability of cropping systems. In this program, I will conduct the fundamental research on to investigate how organic amendments, for example, manure, to regulate soil organic nitrogen, soil organic matter stability, lay biocarbon and nitrogen pool, and nitrogen transformation process, microbial activities and communities, and also root characteristics. Meanwhile, I will also conduct applied research to evaluate the efficiency of the use of organic amendments in improving soil fertility and crop yield. Increase soil carbon sequestration, soil seasonal nitrogen mineralization, nitrate leach, and gas emissions. After this, I will incorporate both of the fundamental research results and applied results into a process-based model to improve the model and predict the crop yield and the environmental impact of the different cropping systems. Based on the model outcomes, the application guidelines for the use of organic amendments will be developed to increase soil productivity. The cropping systems I would like to work with in the future will be annual crops such as corn, wheat, soybean, and perennial crops such as hay, turf grass, apple, and peach. I have spent a lot of time in my past research life to work on developing nutrient management by focusing on nitrogen cycling. I believe my background and my vision will help me to develop a research program, like innovative and collaborative research program to address the future of the agriculture needs. At the end, I want to thank all the funding agencies and all the members in Howard's lab and all the growers I work with and all my co-workers and my conference co-organizers. And also thank you all for your attendance today. Yeah, this picture I was took like 2 years ago. Like this is the rice field I grew up with. Every summer I spend a lot of time to work in this field, and you know, to harvest the rice with this knife and hand. It's under like 100 degrees and about 70 humidity. It's super hot, and I don't want to work on that anymore. But so that's why I work here, and I want to, you know, tell the farmers we got a better way to do that. Yes.
In the first part of your study, where you showed the nitrification, I might have missed it, but I was curious. The soil organic carbon levels in the soil, whether it's representative of other alkaline soils, whether it's low, high.
Okay. So the question is, what's the soil carbon content in the soil, which I worked for nitrifier denitrification study. So that soil is the clay loam, which has the carbon like 1.2 to 1.5%. It's not very high. It's just like average carbon content.
You think this process might be more or less important than higher soils that higher carbon content?
I think this process probably will be a little bit higher in the higher carbon content soil. The reason for that is because in the higher carbon content soil, the microbial activities is relatively higher than lower carbon content soil. And the oxygen will be consumed faster in the soil, and which will promote the nitrifier denitrification process. Mm-hmm. No. So your question is why I didn't see the increase of nitrous oxide emissions from the increased amount of the compost applied in the field. That's kind of like very interesting thing, because we did expect that should have higher nitrous oxide emissions from the field, which we apply more compost. But like what I think is because in California soil, we have relatively high nitrate, you know, content in the like nitrate, like nitrogen in the soil. So the amount of the compost which we applied actually is not reach the level can affect nitrous oxide emissions from the field observation. Yeah, possibly. Like, for example, like iron, like which I found, because we did have certain amount of the iron in the compost when we applied into the soil. So that could be the, you know, the reason to affect the final of compost. And also probably other kind of reasons like pH change, because the compost did increase the soil pH. But like if you didn't put enough compost to increase the pH to the point which will affect the nitrous oxide emissions, probably you will not see the significant outcomes from that. Yes. The CN ratio of the compost is about like 15, like 20 to 1, like 20 to 1. It's a yard waste, so it's mainly from the plant residues. Yes. Actually, I cannot quite remember the value of the iron which we found there. Actually, it's just like the normal value which we found in the soil. But it's an interesting thing. It's very interesting thing. Is like we did extract the iron with two methods. One is like with pyrophosphate, which represents the iron combined with organic matter, and one is like with acid hydroxylamine, which represents a mineral like iron in the soil. And we only find the effect of the the pyrophosphate extracted iron has significant impact on nitrous oxide emissions. So that means only the iron which combined with organic matter, that one can affect the nitrogen cycle process, not the mineral iron in the soil.
So you didn't mention the iron effect in
Yes. Yeah, because I didn't know. I mean, from what I understand, in Kentucky, we have a lot of biosolids, and also we have a lot of contaminated soil. I think in these products, the iron content is relatively high. So in Kentucky, I'm thinking about if we talk about the nutrient management, especially about like nitrogen cycling, iron would be a significant factor contribute to the final decisions which we are going to make. Yes. Yes. I'm going to show you these slides, and that will tell you very. So there are two mechanisms which I assumed will affect nitrous oxide emissions. First is the biotic process. In biotic process, the iron will affect the activities of nitrifiers and denitrifiers, and then affect nitrous oxide emissions. From this graph, from this picture, we can say iron is a cofactor in the ammonia oxidation. I mean, ammonia oxidizers, this enzyme, they need iron. And in hydroxylamine, like hydroxylamine oxides to nitrite, they need iron too. In all this, like the this like nitrite decompose to denitrified to nitric oxide and the nitrous oxide. They all need iron to be as a cofactor to impact the enzyme activities. So this is the first mechanisms. The iron could have the white iron have influence on nitrous oxide production. And the next one is first the iron, under certain conditions when we have no oxygen, iron could affect combined with ammonia to oxidize ammonia to produce this nitrite or nitrate or dinitrogen gas. This process we call the phenomox. So this is the first raw iron could get into the nitrogen cycle. And the second role is like the iron could be reduced to iron 2, and the same mechanisms through the nitrite denitrification. And also in the nitrate process, iron 2 can also get into the could also react with nitrite and to finish the denitrification process. So this is kind of like a circle of how the iron 2 and iron 3, how they change and to impact the nitrous oxide emissions. And yeah, this is these two mechanisms. Yes. It's the study which you mentioned is about the effect of nitrogen substrate, like nitrogen concentration, that experiment, right? Yeah. This is ammonia sulfate. Yes. So those are really high nitrogen. You mean in the field, if that will influence the results?
Well, yes, in the lab.
Yeah. Well, I do. This is a very interesting question. So the reason why we choose this very high concentration is because in the field, when we do the banding application, when we band the fertilizer, we did find this high concentration of ammonia in the soil. But if in the lab, I understand it's like if we apply this much compost, this much of the ammonia, that will change the soil characters. For example, pH and even like microbial activities. Yeah, that's kind of like a part of this study. Like how this kind of high concentration of ammonia will affect the soil process, and that reflect what happened in the field in the situation which we have this banding application of the fertilizer. Yes.
Do you have any knowledge of the state of technology regarding the use of substitute processes, behavior process for making some of these rare earth metals on farm and then commercial level production methods for making?
So your question is if we have some method to reduce the fertilizer production. Is that correct? So I think we can increase the biologically nitrogen fixation to versus like the industrial ammonia fertilizer production. Unfortunately, we have to say it's like we have to use fertilizer to keep our crop yield and to feed the people in the world. But if we can grow the crops which can fix more nitrogen into the soil through the biological process, that could meet the potential to decrease the nitrogen input through the fertilizer set. So, thank you. Yes.
So you put that nitrous oxide gas on, you put that nitrate leaching or nitrate release process because nitrate is one of the elements for what?
Yes, I did look into the nitrate leaching in the study of compost application methods. But the results come out, we didn't have that significant difference between our treatments because in California, we don't have that much rain. And also the irrigation which we did for our study was not like this high enough, the amount of water is not high enough to leach all the nitrate down to our, like the groundwater level. So, yeah, that's my plan in the future if I get this job. So I know in Kentucky we have like a pretty, like the relatively humid climate, and we have like a lot of rains, and so I think the nitrate will be a significant study area in this. And also, I noticed like in the soil in California, we don't have that much nitrogen retained. Like, when every new crop we have to, when we measure nitrogen in the soil, we don't have that much ammonia or nitrate after the previous crop. So that means the nitrogen which in the soil, either like from the residual fertilizer or it's from the mineralized process, either like, lost through the gas or leached through the water, along with the water. So it will be very interesting to see the overall picture of nitrogen, like how much nitrogen go to crop and how much go to the water, how much go to, the atmosphere, and to be able to overview the whole nutrient management practices and evaluate all these practices, how effective that it will help us to resolve our, like our environmental problems and also like increase crop yield.
One more.
Yes, thank you for that question. That's a very interesting question, and it also a very important question for the model perspective. Currently, it's like, unfortunately, we don't have iron this factor in Disney model yet. But I think in the future, if we have more study available about iron, and we could potentially, you know, like to start to build the new soil process in Disney model to simulate what we find